In 2019, a fully loaded fuel tanker slid off an ice road in Yakutia, Russia, and sat untouched for 3 months. Nobody could reach it. 7,000 miles away, a ship designed to carry other ships swallowed an entire river barge whole, then crossed 2 oceans without stopping. These are not isolated oddities. They are symptoms of a global network of transport operations so extreme, so dangerous, and so far beyond normal engineering limits that most people never learn they exist. The answers behind these operations are stranger than the questions, and every entry ahead proves it. Aldan River Ferry Crossing, Yakutia, Russia. The Aldan River Ferry in Yakutia operates just 114 days per year. The rest of the time, ice either blocks the crossing entirely or turns the river into a frozen highway that trucks drive across at their own risk. The ferry ramp sits at a steep 18-degree angle, coated in river silt and ice melt, that turns every boarding attempt into a physics problem with real consequences. Drivers hauling fuel and supplies to remote Yakutian villages have no other crossing point for over 200 miles in either direction. The fifth wheel coupling on each truck, that rotating plate connecting cab to trailer, must sit in an exact position to allow the cab to tilt sharply downward on the ramp, without the trailer's front edge smashing into the cab roof. Move it forward even 4 inches, and the steering geometry collapses. The driver loses the ability to correct on the slick metal ramp surface. In summer, water levels shift daily. The ferry operator adjusts ramp angle each morning based on river depth, meaning drivers face a different entry challenge every single trip. You hear the metal ramp groan under 40 tons of diesel truck. You feel the cab nose pitch forward at an angle that makes your hands lock on the wheel. The rear tires spin once, twice, then catch. Yakutian supply drivers make this crossing dozens of times each season, because the villages beyond depend entirely on what they carry. Medicine, heating fuel, food staples, all of it funnels through this single point. One stalled truck on that ramp blocks the entire crossing for hours. In a region where summer lasts 10 weeks, every hour matters. The Aldan crossing is dangerous enough in calm weather, but what happens when an operation involves a load 20 times heavier and a boat built in 1952? If this kind of raw, real-world transport detail is what you come to explore danger for, a quick subscribe locks in every future video the moment it drops. SS Badger Heavy Load Transit, Manitowoc, Wisconsin. Picture a calm summer morning on Lake Michigan. The SS Badger sits at her dock in Ludington. 410 feet of coal-fired steel, the last operating coal-powered steamship on the Great Lakes. She looks like a postcard. White hull, American flags, tourists lining the upper deck with coffee cups. Now picture what rolls up behind those tourists. A 198-foot industrial rig riding a custom lowboy trailer, tipping the combined scale at 350,000 pounds. The Badger's vehicle deck was designed in 1952 for standard cars and small trucks. It was never engineered for this. The load clearance on each side is measured in single-digit inches. Dock workers guide the driver with hand signals because mirrors are useless at this width. The truck creeps aboard at less than walking speed. Every tire placement is calculated against the ship's center of gravity. Loading asymmetrically could create a list, a permanent tilt that compounds in open water. The crossing to Manitowoc takes 4 hours across 60 miles of open lake. Wind gusts on Lake Michigan regularly hit 35 knots in shoulder season, generating swells that shift unsecured cargo. Once the Badger docks in Manitowoc, the real challenge begins. The rig must navigate through town on streets originally platted in the 1800s. Turns that a standard semi takes in one sweep require 3-point corrections for this load. Power lines must be temporarily raised. Intersections are shut down with police escorts. The route through town covers just 2.3 miles, but takes over 90 minutes. The SS Badger has carried oversized loads like this for decades, because the alternative is a 400-mile detour around the bottom of Lake Michigan. That math keeps the Badger relevant, and keeps her crew managing loads her builders never imagined. Somewhere ahead, a transport crew faces a challenge that makes Lake Michigan look like a bathtub. Andes Mountain Pass, excavator transport, Peru. A 48-ton excavator chained to a heavy-duty hauler is crawling through a Peruvian mountain pass at 14,800 feet above sea level. The road is unpaved. It is 9 feet wide. There is no guardrail. The drop to the valley floor measures 2,600 feet, roughly 5 times the height of the Washington Monument. At this altitude, diesel engines lose approximately 30% of their rated horsepower due to reduced oxygen density. The truck's turbocharged engine is gasping for combustion air while hauling a combined load exceeding 90 tons on a grade that averages 9%. Braking systems generate enormous heat on the descent, and brake fade at this altitude is not a possibility. It is an engineering certainty that drivers must manage actively. The excavator's bucket hangs low, nearly touching the road surface. This is deliberate. Operators position it as a counterbalance and emergency ground anchor. If the hauler begins sliding toward the edge on loose gravel, the bucket operator can dig the teeth into the road surface to arrest the slide. It has saved rigs on this route before. You hear loose rock pinging off the undercarriage. You see the left rear tires riding within 18 inches of nothing. The air is thin enough that your breathing quickens, even sitting still. Dust from the wheels drifts into the canyon and takes 4 full seconds to disappear. That is how deep the drop is. Mining companies in the central Andes depend on this route to move heavy equipment between job sites. Paved alternatives add 200 miles and 3 extra days. Drivers accept the risk because the pay for a single mountain crossing exceeds a full week of flatland hauling. Would you trust your nerves on a 9-foot road? With no rail and a half-mile drop? Tell Explore Danger in the comments, yes or no, and why. German Autobahn Transformer Convoy, Kubler 296-ton haul. A 296-ton electrical transformer does not roll down a German highway by accident. It moves because an entire region's power grid depends on it arriving intact. The Kubler heavy transport team loaded this single transformer onto a rig that brought total convoy weight to 528 tons, heavier than a fully loaded Boeing 747 at takeoff. The pulling power comes from a MAN TGX 41.680, an 8-axle tractor unit producing 680 horsepower. Behind the transformer, 24 Scheuerle intercombi axle lines spread the load across 192 individual tires. Each axle is independently steerable by hydraulic remote. A second man unit pushes from behind, adding braking force on downhill grades and additional torque on inclines. German federal regulations require convoys above 200 tons to travel only between 10 p.m. and 5 a.m. on pre-approved routes. Every bridge on the route must be structurally assessed in advance. Traffic signals at intersections are manually overridden. The convoy moves at 4 miles per hour through urban sections and 12 miles per hour on open highway. The total journey of 85 miles takes 3 full nights. Standing beside the road as it passes, you feel the asphalt vibrate before you see the headlights. The sound is not engine roar. It is a low, continuous hum from 192 tires pressing into the road's surface. The ground itself seems to sag slightly as the axle lines roll past. German heavy transport crews train for 2 years before qualifying for loads above 100 tons. The Kubler team has moved transformers across Europe for over 4 decades. They do it because electrical infrastructure cannot be built on site. It must travel to where it is needed, no matter the size. That statistic, 528 tons rolling through German streets at walking speed, is the kind of number that deserves a moment. If this level of detail is why you watch, leaving a like helps this video reach more people who appreciate real engineering. Zillertaler Timber Convoy, Switzerland. What does it take to move 300 tons of raw timber across some of Europe's most winding mountain roads? The Schutt Transport Company tackles this question on every run toward Zemberg, Switzerland, hauling loads that outweigh most residential buildings through alpine passes built for horse carts. The convoy consists of multiple heavy trucks running in formation, each carrying between 28 and 40 tons of dressed timber. Swiss mountain roads in the Zillertal region average 11 feet wide, with switchback turns that force a loaded truck to use every inch of pavement, and sometimes the shoulder. Gradient changes hit 12% on certain stretches, steep enough that a fully loaded rig builds dangerous momentum. Within seconds of releasing the brake. Swiss law limits timber convoy speeds to 20 kilometers per hour, about 12 miles per hour, on mountain roads. Despite this, brake temperatures on long descents regularly exceed 500 degrees Fahrenheit. Drivers rely on engine braking through low gear selection and exhaust brakes that create back pressure in the engine to slow the truck without touching the foot brake. You smell hot brake dust and pine resin mixing in the mountain air. The trailer groans through each switchback as the logs shift slightly against their chains. Through the windshield, you see the next hairpin turn approaching, with a stone wall on one side and a 400-foot forested slope on the other. Local sawmills depend entirely on these convoys. Rail transport in the narrow Zillertal Valley was decommissioned decades ago. The timber must move by road, or it does not move at all. Drivers make this run year-round, including winter months when ice adds another layer of risk to every curve. But not every timber operation has paved roads to work with. The next entry happens on terrain where roads do not exist at all. If the sound of 300 tons of timber groaning through alpine switchbacks gives you a sense of scale, imagine what happens in the frozen forests of Siberia. Drop a comment with your guess. Yakutia Ice Roads, Siberia, Russia. The Yakutia Ice Roads stretch over 1,200 miles across frozen rivers and tundra in northeastern Siberia. Surface temperatures drop to -76 degrees Fahrenheit. At that temperature, Rubber tires become brittle. Steel becomes fragile. Diesel fuel thickens into gel unless treated with Arctic-grade additives. Trucks travel in convoys of 3 to 5 vehicles, spaced exactly 230 feet apart. This spacing is not arbitrary. It prevents harmonic resonance in the ice. When heavy trucks travel too close together, their combined weight creates synchronized pressure waves beneath the ice surface that can crack a frozen river in seconds. At 40 tons per truck, the margin between safe passage and catastrophic breakthrough is measured in vehicle spacing, not ice thickness. Drivers carry survival kits rated for 72 hours. If a truck breaks down between stations, the nearest help may be 18 hours away by tracked rescue vehicle. Stepping outside the cab at -60 exposes bare skin to frostbite in under 2 minutes. Breathing the open air burns the throat and lungs almost immediately. You hear the ice singing, a deep, resonant cracking sound that travels for miles. Experienced drivers know which sounds indicate settling, and which sounds mean get moving now. Yakutian villages north of the Arctic Circle receive their entire annual supply of fuel, food, and building materials during the ice road season, roughly 100 days from late November through early March. Miss that window, and communities face rationing until the next freeze. Drivers earn premium wages but accept the reality that every season, trucks go through the ice. The Lena River section alone has claimed dozens of vehicles over the past 2 decades. The ice roads are survival infrastructure for 100,000 people. No alternative exists. No alternative is being built. That 72-hour survival kit is not a precaution. It is a statistical necessity. Stories like this are why Explore Danger exists. If you agree, a like is the simplest way to say so. Norwegian wind turbine blade transport. A single wind turbine blade measuring 230 feet long is making its way through a Norwegian coastal storm. Rain drives sideways. Visibility drops below 200 feet. The blade, mounted on a specialized extendable trailer, catches crosswinds like a sail, generating lateral forces that can push the entire rig off the road. The trailer uses a rear-steered axle system, controlled by a technician riding in a chase vehicle behind the load. Every curve requires coordinated input. The tractor driver handles the front. The chase vehicle technician steers the rear axle set by remote. On tight coastal switchbacks, the blade tip sweeps across the opposing lane with less than 3 feet of clearance from rock walls. Norwegian Coastal Route 17 features sections where wind speeds exceed 55 miles per hour during autumn storms. The blade transport teams monitor weather in real time and have a 40-minute decision window to either commit to a stretch or pull over at a designated wide spot. Once committed, on certain single-lane bridges, there is no turning back. You feel the truck shudder as a gust hits the blade broadside. The trailer tires chirp sideways on wet asphalt. Through the rain-streaked windshield, you see the blade tip disappear into fog ahead. You cannot see how far it extends beyond your vision. Norway's commitment to wind energy means 500 to 600 blade transports per year through terrain like this. The country's fjord-carved coastline offers no flat, straight alternatives. Every blade that reaches its mountaintop turbine site arrives because a driver and chase crew fought geography and weather for every mile One mistake in those crosswinds, one gust timed with a curve, and 230 feet of composite material becomes a roadblock that shuts down an entire coastal route for days. Ahead, a recovery operation unfolds in a place where falling off the road means something far more permanent than a traffic delay. Bolivian Death Road Truck Recovery. North Yungas Road in Bolivia earned its name honestly. Between 1999 and 2006, an estimated 200 to 300 people died annually along this 43-mile stretch carved into the Andes. The road averages 10 feet wide. The drop is 2,000 feet. There are no guardrails for most of its length. When a truck overturns on North Yungas Road, recovery is not a tow truck operation. It is an engineering project. Cranes cannot access most of the road. It is too narrow and the surface is too unstable for outriggers. Recovery crews use manual winch systems anchored to rock faces, pulling overturned vehicles upright 1 inch at a time over 8 to 12 hours. 2 excavator operators working in tandem can right a 20-ton dump truck using bucket leverage and cable tension. Their machines sit on a road surface that crumbles at the edges. One operator positions the bucket under the truck's frame, while the other pulls cable tension from the opposite side. The coordination must be exact. Too much force from either side sends the truck, the excavator, or both over the edge. Standing on North Yungas, you look down and see clouds below you. The air smells of wet earth and diesel exhaust. Every vehicle that passes forces you flat against the rock wall. You feel the road vibrate under each tire. Bolivian communities in the Yungas Valley depend on this road for coca leaf and citrus transport, the economic foundation of the region. A newer bypass road opened in 2006, but many truckers still use North Yungas because the bypass adds 4 hours and significant fuel cost to every run. The economics of survival override the mathematics of risk. It is that simple and that permanent. 200 to 300 lives per year on a single 43-mile road. That number is not historical. For many families in the Yungas Valley, it is deeply personal. If content that treats these realities with honesty matters to you, sharing this video is the most direct way to support it. Jamaica Flat Bridge, Heavy Haul. An International 9,300 haul truck is pulling a 38-ton bulldozer across a flat bridge in rural Jamaica. The bridge was built in the 1970s for standard vehicle traffic. Its posted weight limit is 15 tons. The combined load crossing it right now exceeds 60. Jamaican rural infrastructure was designed for an agricultural economy, not heavy construction logistics. Flat bridges, low-profile concrete spans with no arch support, rely entirely on slab strength to bear loads. When a load exceeds design capacity by 400%, the concrete does not crack dramatically. It deflects, bowing downward in the center by fractions of an inch that accumulate with each crossing until structural failure arrives without warning. The International 9300 is a Class 8 heavy hauler with a 550 horsepower Cummins diesel and a reinforced steel frame. The driver crosses at a crawl under 3 miles per hour to minimize dynamic loading. Dynamic load is the additional force generated by a moving vehicle's momentum, and at speed, it can multiply the effective weight on a bridge by 20 to 30%. You hear the concrete groan beneath the tires. You see hairline cracks in the bridge surface that were not there last season. The river below is shallow, maybe 8 feet deep, but the rocks in the riverbed would destroy a cab instantly in a collapse. Construction firms working on Jamaica's expanding resort and infrastructure projects have no alternative routes in many rural parishes. The bulldozer must cross this bridge because the next bridge, rated for heavy loads, is 45 miles away on unpaved mountain roads. Every crossing is a bet against cumulative fatigue in 50-year-old concrete. The bridge does not announce when it has had enough. We are not even halfway through this list, and the loads ahead make 60 tons feel like a warm-up. Yekaterinburg fuel tanker ditch recovery, Russia. In the frozen outskirts of Yekaterinburg, Russia, a 26-ton tanker truck loaded with diesel fuel lies tilted at 40 degrees in a roadside ditch. The temperature is minus 22 degrees Fahrenheit. The truck has been there for 6 hours. The diesel inside is worth approximately $35,000. And every minute it sits, the risk of a fuel seam rupture increases. The recovery crew deploys a Volvo FH16 heavy-duty wrecker, rated for 50-ton pulls. Steel cables rated at 75 tons are anchored to the tanker's frame at 2 points, the front axle mount and the rear chassis crossmember. Pulling from a single point would twist the frame and risk splitting the tank. The wrecker's hydraulic winch generates 30 tons of continuous pull force. The operator increases tension in increments of 2,000 pounds, pausing between each increase to check cable alignment. At minus 22, steel cables lose approximately 15% of their rated flexibility. A sudden shock load on a cold cable can cause a snap that sends broken steel whipping through the air at lethal speed. You hear the cables creak as tension builds. The tanker groans and shifts 1 inch, then stops. Frozen mud grips the undercarriage like concrete. The wrecker engine screams at full throttle. Then the tanker lurches, rises 6 inches, and begins the slow crawl back onto the road surface. Russian long-haul fuel transport operates year-round because heating fuel demand peaks in winter, exactly when road conditions are worst. Drivers on the Yekaterinburg-Tumen corridor haul 100,000 tons of diesel annually through conditions that turn routine delivery into heavy rescue operations multiple times per month. One cable snap during that pull, and the recovery crew is in the path of 75 tons of stored energy, releasing in a millisecond. One of the companies to figure at this moment. One cable snap during the pull inform. Content like this does not get made without research. If the depth matters to you, subscribing tells us to keep going deeper. Brazilian rotor transport to Belo Monte Dam. A single hydroelectric rotor weighing 316 tons is traveling overland through the Brazilian state of Pará. Its destination is the Belo Monte hydroelectric plant on the Xingu River, one of the largest dams on Earth. The journey covers 620 miles and takes 90 days. The rotor sits on a modular hydraulic trailer with 52 axle lines. Each axle is independently height adjustable. To maintain perfect level across terrain that includes unpaved logging roads, single-lane bridges, and river ferry crossings. The total convoy, rotor, trailer, pulling trucks, support vehicles, stretches over 400 feet and weighs nearly 500 tons combined. Road preparation begins months before the rotor moves. Engineers survey every mile, reinforcing bridge decks, widening curves, and removing overhead obstructions. Entire sections of jungle road are regraded to to handle the axle loading. In some stretches, the convoy creates its own road because none exists. You feel the heat first. Pará averages 95 degrees with 90% humidity. The trailer tires sink into softened asphalt on paved sections and leave ruts 4 inches deep. In unpaved stretches, red laterite dust coats everything within 200 feet. The convoy moves at 2 miles per hour through the worst sections. And the vibration from 52 axle lines rolling over rough ground is constant and bone deep. The Belo Monte Dam powers 11 million homes across northern Brazil. Without this rotor, one of the plant's generating units sits idle. The economic pressure to complete delivery is measured in millions of dollars per week of lost generation capacity. Workers along the route camp in temporary stations, maintaining trailer hydraulics and monitoring road conditions 24 hours a day for 3 straight months. If the rotor tips, shifts, or drops during transit, there is no crane in the Amazon basin large enough to recover it. 90 days for 620 miles. That is not a transport operation. It is an expedition. If this level of detail is new to you, you're exactly where you should be on Explore Danger. LKT-81 Turbo Mountain Logging Slovak Carpathians. The LKT-81 Turbo is a Czechoslovak-designed forestry skidder built for one purpose: dragging massive timber out of mountains where no road exists. Its turbocharged diesel produces 135 horsepower and 420 Newton-meters of torque, all delivered through a 4-wheel drive system with locking differentials on both axles. It weighs 9 tons empty and can winch loads exceeding 12 tons up slopes steeper than 40 degrees. In the Slovak Carpathian Mountains, logging crews work at elevations between 3,000 and 5,000 feet on terrain covered in loose shale, root networks, and seasonal mud that can swallow a tire to the axle. The LKT-81 claws its way uphill using a combination of tire grip and its rear-mounted winch drum, which holds 260 feet of steel cable rated for 14 tons. The operator sits in an open cab with minimal rollover protection. When pulling a 10-ton log bundle downhill, the LKT-81 becomes a 21-ton unit on a slope, where gravity wants to accelerate everything toward the valley floor. Braking is managed through engine compression and a mechanical drum brake that heats rapidly on sustained grades. You hear the engine bark as it fights for traction. The steel cable behind the machine vibrates with tension, a deep humming note that changes pitch when the load shifts. Mud sprays from the tires in thick sheets. The smell is diesel exhaust mixed with freshly cut spruce. Slovak logging communities in the Carpathians have used machines like the LKT-81 since the 1970s. Modern alternatives exist but cost 3 to 4 times more. For small-scale family logging operations, the LKT-81 remains the only economically viable option. Operators pass driving knowledge from father to son because no formal certification program exists for this machine. One snapped winch cable on a 40-degree slope, and 10 tons of timber becomes an uncontrolled projectile aimed downhill. Think about that operator in an open cab with no rollover cage. Now consider that the next entry involves a load 25 times heavier on an even more unforgiving route. Schwantner Turbine Tower Transport, Germany. P. Schwantner Logistik moves wind turbine tower sections through German mountain roads that were never designed for loads this size. A single tower section measures 65 feet long, 14 feet in diameter, and weighs 80 tons. The trailer carrying it uses adjustable axle steering. Each axle set rotates independently to navigate curves that would be impossible with fixed axles. The route from manufacturing plant to wind farm installation site crosses through the Swabian Alps, where road grades reach 10% and curve radii tighten to 50 feet. At those dimensions,
The tower sections overhang on tight curves.
extends 12 feet beyond the road edge. Schwanner crews position spotters at every blind curve to halt oncoming traffic and confirm clearance before the driver commits. Load balancing on a cylindrical object this size requires constant hydraulic adjustment. The trailer's suspension system maintains level within 0.5 degrees using onboard sensors and automatic leveling valves. A 1-degree tilt at 14 feet of diameter creates a lateral force shift of nearly 3,000 pounds, enough to upset the trailer's stability on a crowned road surface. You see the tower section emerging from a fog-covered valley road, its white surface ghostly against the dark forest. The trailer tires hiss on wet pavement. You feel the ground pressure from 80 tons rolling past at 6 miles per hour. The air displacement as the cylinder passes pushes you back a half step. Germany's Energiewende, its transition to renewable energy, requires approximately 1,800 new wind turbines installed per year. Every single one of them arrives as oversized cargo on roads shared with everyday commuters. Schwanner alone completes over 200 tower section transports annually. A 3,000-pound lateral force shift on a wet, crowned road. The engineering that prevents disaster operates in fractions of a degree. This is the precision that separates a successful delivery from a catastrophe. And if you appreciate it, dropping a like takes 2 seconds and makes a real difference. Shipyard Heavy Module Move, Rox's MAN FE 600A. The Rox's MAN FE 600A is a self-propelled modular transporter, an SPMT, designed to move objects so heavy that conventional trucks cannot physically carry them. Each module contains 6 axle lines with 4 tires per line, giving 24 tires per module. For a major shipyard component move, multiple modules link together into a single platform controlled by one operator with a handheld remote. In this operation, a 400-ton ship module is being moved 1,200 feet across a shipyard in Bremerhaven, Germany. The linked SPMT platform uses 12 modules, 288 tires total, to distribute the load so that ground pressure per tire stays below 90 pounds per square inch. Without this distribution, the module would crack the shipyard's reinforced concrete surface. Each tire is independently suspended with hydraulic height adjustment, accurate to 1/10 of an inch. The operator walks beside the platform, monitoring a display that shows real-time load distribution across all 288 contact points. A weight shift of 5% to one side triggers an automatic leveling response. The movement sound is strange. Not an engine roar, but a deep hydraulic whisper, mixed with the quiet rolling of 288 rubber tires on concrete. The platform moves at 1.5 miles per hour. You watch something the size of a 4-story building glide past with eerie smoothness. Shipyards operate on construction schedules measured in weeks, not months. A single day of delay in module positioning can cascade into contract penalties exceeding $500,000. The SPMT operator carries that pressure with a handheld controller no larger than a laptop. If the platform tilts beyond 2 degrees during transit, the module's welded connections experience shear forces they were not designed to absorb. The repair cost exceeds the cost of the entire transport operation. 288 tires, 1 handheld remote, and a $500,000 penalty for being late. That combination defines modern shipyard logistics. And most people never know it happens. If you are learning something new with every entry, Explore Danger has a lot more coming. Subscribe to catch all of it. Russian oil field drilling rig convoy. Moving a mobile drilling rig across Russia's western Siberian oil fields requires dismantling it into 7 separate loads, each weighing between 30 and 55 tons. The convoy stretches a quarter-mile long. The route crosses frozen tundra, temporary ice bridges, and unimproved roads that exist only as GPS coordinates. No pavement, no markings, no shoulders. The lead truck hauls the rig's mast section, a 90-foot steel tower folded into transport position. Behind it, the substructure, mud pumps, generators, and pipe racks follow on specialized trailers. Each load is secured with chains rated at 70 tons. Fastening protocols require 45 minutes per truck. A single loose chain at highway speed becomes a 200-pound steel whip. Western Siberian oil roads are built on permafrost, ground that stays frozen year-round, but softens in surface layers during brief summers. In winter, the surface is stable, but temperatures hit -50 Fahrenheit. In spring thaw, trucks sink axle deep into mud that freezes around them overnight, trapping vehicles until excavation equipment arrives, sometimes days later. You hear the convoy before you see it, diesel engines echoing across flat, treeless tundra. The air is so cold it burns your nostrils. The sky is a flat gray that makes distance impossible to judge. The rigs look like they are crawling across the surface of another planet. Russia produces over 10 million barrels of oil per day, and a significant portion comes from fields accessible only by these convoys. Each drilling rig relocation costs approximately $2 million and takes up to 2 weeks. Delays due to weather or road failure cost $150,000 per day in lost production. A rig stuck in spring thaw is not just a logistics problem. It is $150,000 burning every 24 hours, with no solution except waiting for the ground to decide. If you have ever worked oil field logistics in Russia, Alaska, or anywhere, Explore Danger wants to hear your story. Drop it in the comments. Trans-Siberian rail freight mishap. In 1998, a rail switch left open on the Trans-Siberian Railway sent a loaded freight consist onto a siding at 40 miles per hour. The train carried 3,200 tons of mixed cargo across 58 cars. The siding was 600 feet long. The train needed 2,400 feet to stop. The math was simple, and the result was inevitable. Rail switch errors account for approximately 12% of all freight rail incidents in Russia annually. The Trans-Siberian Railway spans 5,772 miles, the longest railway line on Earth, and processes over 100 million tons of freight per year. At that volume, a 12% incident rate translates to thousands of switch-related events per decade. The siding derailment scattered cargo across 400 meters of track
and took 72 hours to clear. During those 72 hours, all eastbound freight traffic on that section halted. The economic impact rippled across supply chains, serving cities 3,000 miles in both directions. Perishable goods spoiled. Manufacturing inputs arrived late. The cost exceeded $4 million before the track was reopened. Stand at a Trans-Siberian crossing point, and you feel the ground shake 3 full seconds before the train becomes visible. The sound builds from a low rumble to a wall of noise. Each car passes with a rhythmic metallic pulse, steel wheels on steel rail repeated 58 times. At 40 miles per hour, the full train takes over 90 seconds to pass a single point. Russian logistics depends on the Trans-Siberian for goods that cannot practically move by road. Bulk minerals, timber, petroleum products, and heavy machinery. For cities east of the Urals,
Rail is not one option among many. It is the only option at scale. One switch. One error. 3,200 tons with nowhere to go. The fragility of systems we assume are reliable is a theme that runs through every transport operation on this list. 3,200 tons redirected by a single open switch. Infrastructure at this scale operates on trust. Trust that every small component works perfectly every time. When it doesn't, the consequences travel thousands of miles. If that thought resonates, a like helps this video find more viewers who think critically about the systems that move the world. Patagonia, overturned dump truck excavator recovery. A loaded dump truck carrying 22 tons of crushed rock has overturned on a construction haul road in Argentine Patagonia. The truck lies on its side in a drainage ditch, with its cargo spilling across the road's surface. Wind speed is 45 miles per hour, standard for Patagonia, where gusts regularly exceed 70. 2 excavator operators position their machines on opposite sides of the overturned truck. The technique is called a dual-point lift. One excavator hooks the truck's upper frame rail, while the other pushes from beneath the chassis. Combined, the 2 machines generate approximately 60 tons of lifting force. The overturned truck weighs 38 tons loaded. The margin is tight. The ground beneath the excavators is compacted gravel over clay. Stable enough when dry, but unpredictable when the Patagonian wind carries moisture from approaching weather systems. If the clay layer softens during the lift, an excavator's tracks can lose purchase and slide toward the ditch, pulling the operator directly into the path of the falling truck. You hear the wind before anything else. It does not gust, it pushes continuously, a wall of cold air from the Antarctic south. The excavator booms creak under load. Chains connecting the truck to the excavator bucket rattle against steel. The dump truck rocks once, then rises, slowly, unevenly, fighting gravity and wind simultaneously. Patagonian construction projects operate within narrow weather windows. Road building and mining operations in the region lose an average of 90 working days per year to wind alone. Recovery operations that would take 2 hours in calm conditions stretch to 6 or 8 when crews must account for sustained gale-force winds. Recovery in Patagonia is not just about lifting power. It is about reading the wind like a sailor and knowing when the next gust is coming. Most recovery operations happen in controlled conditions. But what happens when the machine being recovered is part of a system designed to reshape the Earth itself?
TESMEC 1475, Trencher Storm Drain Operation. The Tesmec 1475 is a 54-ton chain trencher that cuts continuous trenches up to 8 feet deep and 3 feet wide through solid ground. Its cutting chain, a continuous loop of tungsten carbide teeth mounted on a steel boom, spins at 140 feet per minute, chewing through clay, rock, and compacted soil simultaneously. Stormwater drainage installation requires precise depth and grade control. The 1475 uses a laser-guided grade control system that maintains trench depth within half an inch of specification over runs exceeding 1,000 feet. At 54 tons, the machine generates ground pressure of 8 pounds per square inch through its wide rubber tracks, low enough to operate on saturated soil without sinking. The cutting chain contacts underground utilities, water mains, gas lines, electrical conduits, with zero tolerance for error. Utility location services mark buried infrastructure before trenching begins, but maps are often inaccurate for older installations. One strike on a pressurized gas main at 140 feet per minute generates sparks and a rupture simultaneously. The explosion radius for a 6-inch main is 100 feet. Standing near the 1475 during operation, you feel vibration through the ground in your feet and knees. The sound is a deep, grinding roar mixed with the crack of fractured rock being expelled from the trench. Dust and debris eject from the trench in a continuous stream.
The chain's teeth blur into a single gray ribbon of moving metal. Municipal drainage projects in the American Midwest rely on machines like the 1475 to install storm systems before seasonal flooding begins. The construction window between spring thaw and first major rainfall is often just 8 to 10 weeks. Delays push installations into flood season, when the trenches themselves become drainage channels, undermining the very roads they run beneath. A gas main strike at 140 feet per minute. No warning, no reaction time. The operator sits 15 feet from the cutting chain and trusts a map that might be decades old. If the engineering precision in this entry impresses you, what is coming next operates on an entirely different scale. We're talking about ships carrying ships across open ocean. Ship-on-ship heavy-lift vessel transport. A heavy-lift vessel does exactly what the name implies. It carries other ships on its deck across open ocean. The method is called float-on, float-off. The heavy-lift ship partially submerges its own deck by flooding ballast tanks until the deck sits 30 feet below the waterline. The cargo vessel is then floated directly over the submerged deck. The ballast tanks are pumped dry, the deck rises, and the cargo vessel is lifted clear of the water, sitting on the deck of another ship like a car on a flatbed. The Blue Marlin, one of the most famous heavy-lift vessels, has a deck area of 51,000 square feet and a deadweight capacity of 76,000 tons. She has transported oil platforms, naval destroyers, and entire offshore drilling rigs across every ocean on Earth. Her deck carried the USS Cole, an 8,400-ton guided missile destroyer, from Yemen to the United States for repairs after the 2000 bombing. The ballast flooding process takes approximately 12 hours. During submersion, stability calculations must account for free surface effect, the sloshing of water in partially filled tanks that can amplify roll and cause capsizing. Every tank is filled in a precise sequence, calculated by naval architects before each operation. Watching from shore, you see a ship sink. The deck disappears, water covers the surface where crew walked hours before. Then slowly, another vessel drifts over the spot and stops. Pumps engage.
The deck reappears, rising under the hull of the cargo ship, lifting it inch by inch until it sits fully clear of the water. The entire process looks like a magic trick, performed at industrial scale. Global oil, gas, and naval industries depend on heavy lift transport for assets too large or too fragile to sail under their own power across ocean distances. A ship that sinks itself on purpose to carry another ship. The engineering confidence required for that decision is extraordinary. Seeing a ship carry another ship challenges your sense of what is physically possible. If you have never encountered this before,
You just found a channel that shows you what most people never see. Subscribe. There is much more ahead. China to Netherlands inland vessel, ocean crossing. An inland river barge built in a Chinese shipyard must reach the Netherlands, 12,000 nautical miles away. The barge was not designed for ocean travel. It has no ocean-rated hull, no deep-water ballast system, and no capacity to survive open sea swells exceeding 6 feet. It was built to float on the Rhine River. Getting it there is the problem. The solution is a heavy-lift vessel that carries the barge as deck cargo across the Indian Ocean, through the Suez Canal, and into the Mediterranean before reaching Rotterdam. The barge weighs 4,200 tons empty. Loading it requires the float-on procedure. The heavy-lift ship submerges, the barge is towed over the deck, and the ship surfaces beneath it. The barge must be positioned within 18 inches of its target location on deck. At 4,200 tons, repositioning after loading is not feasible. Sea fastening, the system of welded brackets, chains, and turnbuckles that locks the cargo to the deck, must withstand forces generated by 30-foot ocean swells. The North Atlantic in winter generates sustained wave heights of 20 to 35 feet. Each wave cycle applies hundreds of tons of lateral force to the sea fastenings. A single bracket failure initiates a cascade, load shifts, adjacent brackets overload, and the cargo goes over the side. The transit takes 42 days. You watch the barge sitting on the heavy lift ship's deck, surrounded by open ocean. A river vessel riding on another vessel, completely out of its element, thousands of miles from any river. It looks surreal and impossible. European inland shipping companies order vessels from China because construction costs are 40% lower. The ocean delivery cost is factored into that savings. The economics work, as long as nothing breaks. 42 days on open ocean, riding on another ship, held down by welded steel brackets against 30-foot swells. The margin between delivery and total loss is the integrity of every single weld. Every entry in this script shares one truth. The global economy moves because people accept risks that most of us never see and never consider. These are not hypothetical dangers. They are daily operations performed by drivers, operators, engineers, and crews who measure their safety margins in inches, degrees, and fractions of a second. The roads they drive have no guardrails. The loads they carry exceed the limits of the infrastructure beneath them. The weather they work in would shut down entire cities. And yet they go, because somewhere, someone depends on what they are carrying. If even one of these operations changed the way you think about how the world moves, this video did its job. Explore Danger covers these realities because they deserve to be seen. Not as spectacle, but as the documented truth of what extreme transport demands from the people who do it.
Share this video with someone who has never thought about what it takes to move 316 tons through the Amazon or carry a ship across an ocean. Awareness starts with knowing it happens at all. Comments. That conversation is the reason this channel exists.